Dr. Pushparaj Shetty, NITK Suratkal. I request sir to kindly come up to the stage, and I request Dr. R. Balaji to felicitate sir with the shawl. Dr. Pushparaj Shetty D is working as a faculty at NITK Suratkal since 2000. He is presently holding the position of professor in the Department of Mathematical and Computational Sciences at NITK Suratkal. He obtained his BE in CSE in 1999 from Bangalore University and ME in CSE in 2005 from Indian Institute of Engineering, Science and Technology, Shivpur. He obtained his PhD from the Computer Science and Application Group, Department of Mathematics at the IIT Delhi in 2014. His research interest areas are in the area of wireless sensor networks, graph algorithms and their application in engineering, cloud computing and HPC. He has successfully guided 5 PhD students and 4 MTech by research students. 2 students are pursuing PhD under his guidance, and he is associate with a number of associations like IEEE Bangalore subsection, and he is senior member of IEEE, member of IEEE Computer Society, senior member of ACM, and life member of CSI and IEI. Dr. Pushparaj also volunteered as chair of IEEE Bangalore subsection for the year 2021. He is additionally holding responsibility as professor in charge of hostels, which hosts about 6,000 plus students. Over to you, sir.
So, yeah, good afternoon all. Very happy to be here for this conference. Thank you, Balaji sir and all the organizers. To start with, the first paper title is an HLS-driven architecture design for the present lightweight block cipher. Author is Atul M and others.
Gopal Pandey, and I am from CSIR Siri Pilani. I am here to present a paper where the contributors are Atul, Diksha, Jugal and M. Santosh. So the title of the paper is an HLS. HLS means high level synthesis driven architectural design for the present lightweight block cipher. So the content of the paper So outline is as. So first we will discuss what is the motivation, why we are going to do this work, what is the importance in the context of public key infrastructure and post-quantum cryptography, and what is the present cipher, what its needs, what is the research gap associated with it, and why we need to do some hardware implementation and new methodology should be adopted for that. And we have performed some experimental analysis. For that, we did some setup basically related to FPGAs. We incorporated FPGA boards and performed all the required simulation synthesis and post-synthesis simulation, and will perform all the job related to this. So motivation, we know that when we form an cohesive kind of infrastructure where pervasive computing is required, like IoT or edge-based devices, where tiny devices are communicating each other in an automated fashion. So here security can be compromised. For that, because these devices are going to be deployed in various kind of application like smart cities, gadgets, biometric data, some medical data recognitions, even bank transactions also. So here we all agree that secure communications is essential. So for implementing secure communication, hardware is the suitable choice, because we know that the block ciphers are mostly suitable for hardware, and where we can provide parallel kind of implementation. So for that, there will be a trade-off between security, cost. Cost means that silicon area, or when silicon area is there, money will also be there. Performance. So there is a trade-off between security, as shown here, security, cost, and its performance. So we need to perform these trade-off between. So we need to have a lightweight kind of structure where all these three can be there. So for that, we have used infrastructure related to public key cryptography, and for block level data transfer, we have used present cipher, which is nothing but it is a 64-bit operand will be there, and data key can be 80-bit or it can be 128-bit. And for this, we have used HDLs for implementation, and for generation of FPGA HDL, which is suitable for FPGA implementation, we have used HLS. HLS is nothing but it is a high level synthesis, and this is the present cipher. It is a SPN kind of cipher where 64-bit data can come in 1D array, and it performs encryption and decryption through some key, and there will be a common controller. So there will be linear layer and secure communication layer, and there will be in each round there will be round key. There are 31 rounds. So what is the research gap? As we can see in this graph, when we are performing at the RTL level, which is the purest form of the hardware, so we can have this green kind of implementation, but it requires a knowledge of hardware, understanding and design VLSI algorithms and its implementation strategy. So we want to have a quick estimation and quick hardware implementation. For that, we need to work at higher abstraction level. So higher abstraction can be high level synthesis approach, and it can also be designed at high level modeling approach. When we use high level modeling approach without bothering of hardware architecture, we can have this kind of implementation, which is shown in the orange color. The hardware was not there in the mind. It has been written like in a C or Python code, and the tool has generated the required hardware. But when we need RTL kind of code, we need to have an architecture in our mind. So the best way is to use architecture aware design and use HLS, high level synthesis, and so that the yellow kind of triangle can become. And our aim is to minimize yellow triangle so that it can merge with the green one. So this is a research gap where high level hardware implementation we need to streamline for the quick abstraction level so that it can also achieve accuracy and quick time to market as needed. So here, this is the architecture which we have described, and the algorithm is standard algorithm where 31 rounds can perform for add round key, S box layers, and some P layer, permutation layer will be there. So HLS controller has been designed at top level. It is a wrapper kind of thing, and at the bottom layer there will be structure for encryption and decryption. We have performed encryption, decryption, and combined unified encryption and decryption. So modeling, we have performed C++ can also be used, and we have used Xilinx AMD Vitis HLS, AMD tool for Vivado, and we have used Zinc 7000 series FPGA for performing, and we have also included this as an IP with AXI bus for ARM core processor. So FPGA implementation, when we performed, we got this kind of resources, and this is the slice count. Latency is 67, and this is the pure implementation. So when we implement as a PSPL implementation, so there will be a resource crunch in terms of we want to have processor which takes a lot of area, and this as an IP, but whole thing can be formed as an SoC. So for SoC, this can be a secure chip where present will be used for the block level cipher, and other ECC or other ciphers can also be used for the public key infrastructure. This is the pure FPGA implementation. Now we are going to perform FPGA level comparison. So as we have discussed about the comparison, so when we write a pure HDL, so like it is a pure architecture driven HDL code where the code is handcrafted at the RTL level using VHDL language. It takes around 221 lookup tables and 224 flip-flops. Latency was 33 because 31 takes it has been taken by the algorithm, one for the initialization and another for the starting of the key generation block. So 31 plus 1 plus 1, 33 clocks are there. So this is the smallest footprint with maximum frequency of 278. So another version which is not aware with this, it is again RTL version. So it is similar kind of implementation where architecture has not been initialized and they took let us say 1 and there will be some increase. But when we have compared this with HLS, this work is also HLS and this is also. So HLS comparison, this implementation is not architectural driven. They have written HDL kind SEEP kind of code, and without bothering of hardware architecture, what will be the implication at the hardware level, how we can use concurrency, other stuff. So they got around this kind of frequency, 125 megahertz, and the LUT is around 466 and flip-flops around 765. But when we write code using this architectural driven design HLS, so we can minimize flip-flop hardware resources also, and we can achieve a good amount of resources. We can save good amount of resources, and latency has also been improved, 67, and maximum frequency is around 224 megahertz. So the proposed implementation has reduced around 38% of LUTs and 51% of flip-flops. It is, and we got improvement in latency around 99%, because we know that how the HLS is writing its lower level implementation. So at that level we works, and maximum frequency we have reduced in comparison to the previous HLS which has been given here. So the conclusion is we have proposed an HLS-driven framework where SOC can be designed. Here, an optimized version of present algorithm has been ported as an IP, where C has been used as a language to model the HLS code, and design and implementation has been performed at the Vivado tool level, and FPGA used as a target device, and it outperforms the previous implementation as given in the previous slide. And we have also we got results comparable to RTL, but not very good result as compared to the handcrafted RTL, but is more or less comparable. But in the future, we are going to minimize that so that it can be comparable, or it can be equivalent to that of pure HDL. And this we have also integrated in a PSPL kind of system where SOC or a complete system with peripheral and connectors can be formed for achieving this kind of thing. These are the references, and this work has been supported by ANRF, and we are working in for a hardware security level project. The title of project is the hardware modeling for secure communication, and the project has been granted by NRF. So we are thank you for that, and thank you. I will be happy to answer your question if is there. Thank you. Yeah.
I want to know how have you implemented the S-boxes?
S-box as a combination circuit, sir.
That is using LUTs or using combinational logic?
Yes, the combination logic.
Then can this be pipeline? Have you tried? No, can this be pipeline? That's what I'm asking. So that throughput can be increased.
Question is not clear, sir.
How the throughput can be increased? By pipelining.
5 by 9. Pipeline. Okay, sir. It is basically a small tiny box, 4-bit S box. So there is no need to store into the memory. If we want, we can also store in. Yes, sir. Rounds are there. Yeah. So it is a iterative process. One S box we have taken and performed 31 rounds iteratively. One S box has been used, a set of boxes. Overlap the operation. Which operation? No, algorithmic dependency is there, because all the operation inside the algorithm is sequential in the nature. Pipelining is different thing. We can perform pipelining. Apart from the pipelining, we have shared the resources at the encryption and decryption. But when we are performing encryption and decryption both, we have shared the resources where pipelining and other stuff has been performed.
You have done both hardware as well as
Yes, sir.
software part.
Yes, sir.
Simulations which you have.
Yes, sir. Hardware, yes. FPGA realization we have performed on the FPGA board.
So in that slide number 10, which you had presented the results.
Yes, sir.
The proposed work is what?
Yeah, this work.
And that improvement is only with respect to the HLS, the third row.
Yeah, because earlier one is the pure HDL. There is no need to compare because it's the purest form. So we want to achieve that form. So because when here we can see the HDL, this RTL requires knowledge of VLSI, knowledge of hardware architecture, and knowledge of hardware modeling using Verilog or VHDL. But nowadays with the advent of the tools and with the computer science background people, if we can achieve the same hardware implementation using C or Vivado, that tools claim and the methodology also. So we want to work at the higher abstraction level. So at this level, we can achieve secure accuracy as can be achieved through hardware realization, and we can perform the modeling effort very high. Basically, we can change the architecture as and when required. So quick time to market is very less here.
So this diagram shows that as you go down, that accuracy
when we go down, accuracy basically increases. And here when we show the architecture design resources, if we take RTL, resources will be optimal, very low. And this is the highest resources because we are working at the higher abstraction level. So we know that resources will be there, but time to market will be very low.
So abstraction and accuracy, they are opposite.
Yes, sir. Yes, sir. When we work at the higher abstraction level, we are going to compromise with the accuracy. But flexibility is there. Flexibility we can change here and there as it required, and we can quickly estimate the performance parameters, design parameters, and also change the hardware architecture as and when required.
Thank you.
Thank you, sir. Thank you. Yes, sir. So final matrix is these, sir. Resources in terms of slices, latency in terms of clock cycles, and maximum frequency because these two depend. And we can achieve this. Power is also a factor. Power consumption is also a factor. So these are the design metrics through which other architectures claim that these are the architectures and these are the parameters. On that parameter, we are comparing our architecture. And it's standard one. This Cipher has been standardized by ISO 2007. Yes, sir. Yes, sir. Through this design method, we change. Even if we work at the RTL level, if there are iterative architecture, we can perform parallel architecture, we can perform hardware loop and roll architecture. So depending upon which design metric for which we are going to target. If we want to save hardware, iterative will be good. If we want to achieve higher performance, parallel architecture will be good. So it depends upon the need and silicon area, because sometimes we are performing some operation very fast, but it depends upon other operations. So why we are going to perform that operation fast? So we can save area, so we can slow down. So it depends upon where we are going to fit this architecture in an amalgamation form with the SOC other components. Thank you, sir. Thank you. After that, when we work at the security application layer, that will perform at that level only. This is the physical layer.